The next step in getting better performance out of our memory consistency model is weak ordering. Notice that with processor consistency, all accesses need to be treated in the same way. If two accesses are executed by the same processor, then they need to be seen in order throughout the whole system. But that's not really the way that synchronization works in most programs. In most programs, you have certain variables that you know need to be updated in the critical section, and anything else you don't rely upon access being serialized to it, so it doesn't really matter the order in which memory is accessed. So all we need to do to improve performance is to divide our memory operations into two categories. The first is synchronization variables, and we need to make sure that those are sequentially consistent, but there aren't very many of them, so it's not going to be that much of a performance hit. Accesses to all other memory locations can be treated as concurrent, and this is called weak ordering. The advantage of weak ordering is that we don't need to propagate accesses that occur during a critical section. Once we do the synchronization and we get into a critical section, we can perform any accesses we want, knowing that no other process can access those variables because we're inside a critical section, which is guaranteed to be exclusive to one process. So we really don't need to worry about where any memory access is seen until it comes time to exit the critical section. And when we do that, we need to make sure that the results are propagated through the system, which means that all of the memory accesses that have occurred in the critical section are seen everywhere in the system. And we have to stop other actions from taking place until that occurs. So the synchronization points are really important here. They need to be sequentially consistent no matter what the cost, but we rely upon there being very few of them to get good performance. And similarly, when we want to enter a critical section, we need to make sure that all previous writes have finished, because the write to the synchronization variable needs to be seen everywhere in the same order. So we need to make sure that all previous writes have finished so we can access the synchronization variable, and then we're inside our critical section. We don't care what happens until it becomes time to exit the critical section, at which time we need to make sure that all previous memory operations have completed, and then we're out of the critical section. So our definition of weak ordering is this: a memory system exhibits weak ordering if accesses to synchronization variables are sequentially consistent. No access to a synchronization variable can be performed until all previous writes have completed everywhere. No data access can be performed until all previous accesses to synchronization variables have been performed. And when I say writes have completed everywhere, that means that if anywhere in the system we load the value that was just written, we try to read the value that was just written, we get the new value. So by doing a synchronization before reading shared data, a process can be assured of getting the most recent values written by other processes before their immediately preceding synchronizations, which means that if another process did a synchronization before you're doing a synchronization, you'll see the values that were written by the other process as late as possible before that previous synchronization. The idea being that if a value was written by that other process after the latest synchronization, then you're not necessarily going to be able to see it until that processor synchronizes again. One limitation is that synchronization is global throughout the whole system, and that means if you're entering a critical section, a process needs to signal that it's entering the critical section, it needs to signal it to everybody, and then it's basically in the critical section until the next synchronization operation. So you can't have multiple synchronizations going on throughout the system and just have them affect the processes that are sharing particular locations. Synchronization affects all processors here. Now this model places a burden on the programmer because the programmer needs to say what's going on. The programmer needs to say, well, this is a critical section. But if you look at OMP, OMP has a pragma OMP critical construct that allows you to say you're entering a critical section. So if you use the right OMP directives in an OMP program, you'll be okay on that. The advantage of weak ordering is that you don't have to keep memory up to date except at synchronization points. Other memory accesses can happen whenever they happen without causing trouble. And if you think about it, when you compile a program and variables are kept in registers, you're not updating main memory. But you've got to make sure that those variables are written back to main memory before anything might happen, like the process gets interrupted or something. Those variables need to be saved when it gets interrupted. The registers need to be saved back to memory. If there was any possibility that other processors would want to read these variables, they couldn't be kept in registers. Processors can live with out-of-date values, providing that they know when to access them and when not to. Here we have a legal sequence under weak ordering. Processor 1 does a couple of writes, then synchronizes. Processor 2 does a couple of reads and then synchronizes. Processor 3 does a couple of reads and then synchronizes. But notice that processor 3 reads the value of x as 1, even though processor 1 has already set it to 2. Now you might think that's not permitted. But remember what I said, that all accesses before the previous synchronization point would be seen, and you wouldn't necessarily see them until you do a synchronization. So when process 1 does a synchronization, process 2 and process 3 does the synchronization, then at that point, process 2 and process 3 are guaranteed to see all of whatever process 1 did before that synchronization point. So the problem that we had here, the apparent problem, is that process 3 reads an outdated value there and process 2 reads an outdated value there. But that doesn't matter at all, because the only thing that's guaranteed by weak ordering is that once you reach a synchronization point, you see all the changes made by other processors before those processors executed their most recent synchronization. One way of putting it is that P2 and P3 haven't reached the synchronization point yet, so they're not guaranteed to get the most recent value of x. Now here's a sequence that's illegal under weak ordering. And if you look at it, you see that process 2 reaches its synchronization point. So after the synchronization point, it's guaranteed to see all the writes that have happened before the synchronization point. The most recent write was the write of 2 to location x, so it should see the 2. If it doesn't, that's a violation. At the hardware level, synchronization can be implemented as acquiring a lock followed by releasing a lock. So before a synchronization, all previous operations must finish, and then no memory operations load or store can occur until the synchronization finishes. Because in a critical section, as I've said before, only one process is inside, so you don't need to worry about anybody else accessing those variables. And outside a critical section, you normally don't care what happens, because if you did, you would have synchronized. Synchronization points are typically operations like fetch and op, which we'll consider in a few lectures, and test and set, which is a very basic hardware instruction for making sure that only one process gets a particular value of a variable before it's changed. The advantage of weak ordering, again, is that all memory operations don't need to be treated as equal. A programmer who wants to synchronize just needs to say this is a synchronization by using pragma OMP critical or something like that, whatever is provided by the language or programming package that they're programming in.